Hello and welcome to this new video. In this video, I'm going to solve exercises 5 to 10 of chapter 2. But before I start, let me solve the last exercise that I gave you in the last video and was solved by Steve. Okay, so this is a classical and a typical question in complex variables. So we have to compute a line integral over a loop and then deduce the value of an improper integral of a real variable. Okay, so here we give the loop. It's half a circle. So we start first by finding the singularities of the function we need to integrate. So this function here inside, it's holomorphic except when z squared plus 1 equals 0. So when z squared equal minus 1, so we have two roots, plus I and minus I. Now usually it's the singularity inside the loop which matters, okay? And I will tell you why. And then we draw a picture. So the picture is like this. We have to apply Cauchy's integral formula, but we have to check, we have to be rigorous. We have to check the conditions of the applicability of Cauchy's integral formula. So we have two ways. First, we write the function we need to integrate as the ratio of a holomorphic function over z minus I. Okay, because why not the other way around? Because I is inside the circle, inside the half circle, inside the loop. Okay. So in order to apply Cauchy's integral formula, f must be holomorphic on an open set in which the loop is homotopic to a point. So we usually have two options here, but two equivalent options. I will present them both. So first way, we find a domain usually, so it's better if it's convex or star convex or simply connected. Now f is holomorphic on C without minus I, but C without minus I is not simply connected. It's not convex, it's not star convex. But if we restrict this domain to this upper half space, okay, so this is the line, and the dashed line in red actually is the line, the horizontal line y equal minus 1/2. Why are we doing this? Because we want to separate the singularity of f from the loop. Okay, so this is one way. It's not the unique way actually. You can take any line you like actually between -1 and 0, strictly included. But for simplicity, I took the line y equal minus 1/2 that separates the loop from minus I. And now omega is actually the upper half plane above the dashed line in red. And this is convex, okay? It's a half plane. And f is holomorphic on omega, okay? If omega is convex, then in particular, it's simply connected. So any loop, not this one in particular, any loop is homotopic to a point. Okay, so this is one way of proceeding. So as we said, omega is convex and therefore simply connected. And so in particular, the loop, our loop is omega homotopic to a point. This is the first condition. Second condition, f is holomorphic on this set omega. And gamma r is a loop in omega. Okay. So we can apply Cauchy's integral formula. And we get this result. Okay. Now, the index of gamma with respect to I is 1. Why? Because gamma is a simple loop, and this will be the case in applications actually. So we'll not consider non-simple loops. So it's a simple loop which is positively oriented and has I in its interior. Okay. So the index is 1. And it's easy to compute f of I for this f. So f was eiz over z plus I. So it's e to the I times itself, which is e minus 1 over 2i. And therefore, the integral we are seeking is pi over e because I simplify by 2 pi I. Okay, so pi times e minus 1 or pi over e. Okay, this is the first way of applying Cauchy's integral formula. There's another way. We take omega now to be c without minus I, okay, on which f is holomorphic, but this is not convex. However, the straight line homotopy joining the loop that I denote in this way, gamma r, this is our loop. I don't care about an explicit formula for gamma r, okay, so this is just half of the circle. This is the straight line homotopy joining gamma r. When s equal 1, we are at gamma r. When s equal 0, we are at gamma r. When s equal 1, we are at 0. Now, this homotopy, or this deformation, if you like, happens in omega. Okay, so this homotopy can never equal to minus I. So it's a homotopy in omega. Okay, and so we can apply Cauchy's integral formula as before. Okay, so the deformation, let me illustrate this homotopy on a picture. So this is my gamma r in green, and by successive contractions, I reach 0. Okay, this illustrates the straight line homotopy. It's a homotopy, if you like, of ratio 1 minus s. Okay, and this homotopy happens in the upper half plane, so it's far from minus I. Okay, and this is what we checked this algebraically actually. Okay, so this is the second way of applying Cauchy's integral formula. So we have to check 3 conditions actually, but the 2 ways are actually equivalent. Okay, so it's the same idea, but written in a slightly different way. So you use the method you like. Okay. Now, so this concludes part A. Now, part B is easy. We write the integral over our loop as the sum of 2 integrals, the integral over the diameter from minus r to r, and plus the integral over the upper half circle, CR. So gamma r is dr star CR, or so we can write dr union CR or dr star CR. So it's the concatenation or juxtaposition or composition of these 2 paths. Now, the first integral, I can compute it directly by using the parameterization gamma of t equal t between minus r and r, and the derivative is 1. We did something similar before. When I separate the real part and imaginary parts, the sine t actually, the integral of sine t vanishes because sine t is odd and t squared plus 1 is even. So when I separate into real parts and imaginary parts, the imaginary part vanishes. So we are just left with the real part. And this converges, actually, I know that this integral is convergent to twice the integral from 0 to infinity of cosine t over t squared plus 1 dt, as r tends to infinity. And the purpose, so don't try to compute it because the purpose is to compute it. So I leave it as it is. And now let us take a look at the second integral over the upper half circle. Okay. Take an arbitrary point in the upper half circle, z. If you write it as x plus iy, y is positive because CR is in the upper half circle. Then e to the iz is e to the ix plus iy. The modulus of eix is 1. So we are left just with e to the minus y because I, right? So the minus comes from multiplying I twice by itself. So what's the numerator here? The numerator is just the modulus of EIZ. Okay? And now since y is positive, the numerator is less than 1. It's at most 1. Now, by the second form of the triangle inequality, the modulus of z square plus 1 is bigger or equal than z square minus 1 in modulus. This is the second form of the triangle inequality. So when we take inverses, we get the opposite inequality. So 1 over the modulus is less than 1 over modulus of z square minus 1. But since z is in CR, the modulus of z is equal to r because we are on the circle. Okay? And okay, this is first thing. So this is very important because this is an estimate of the function inside. If you want to estimate the integral, the second integral, sorry, there's no square here. So this is an error. So we have just to multiply by the length of the circle, of the half of the circle, which is pi r. Okay, so there's no 2 here. And so we succeeded in finding an estimate, a very simple estimate of the integral over the half of the circle. And this, what happens as r tends to infinity? It tends to 0. Okay, and we just have to conclude now. So I rewrite my equation now because I could by part A I computed the integral over the loop. It's pi over I. It's the sum of two integrals. When r tends to infinity, this tends to 0 and this tends to the integral. Okay, and that's it. So this is a typical exercise that we ask in the exam. Okay. Now I have 2 remarks before I move to the exercises. Steve solved this exercise by a slightly different method. He decomposed the function to integrate into simple fractions. And then he integrated each part. Okay, now he took now the function f for Steve is not eiz over z plus I, it's just eiz, which is holomorphic on C, and C is convex. And he checked anyway that gamma r is homotopic to 0 in C, right, by the straight line homotopy. It's not necessarily, when we work on a convex set, we don't need to check because we know that the straight line homotopy will work. Okay. So the first integral is 2 pi I over E, and the second integral is 0. Why? Because minus I is outside, so the index of gamma r with respect to minus I is 0. So when we divide by 2i, we get the result. And he continued in the same way. Now, this is a nice solution. It works very well here. However, it becomes tedious if we want to compute something like this, or eiz over z squared plus 1 to the power n. Okay, and by the way, here's a challenging result. Try to find a formula for eiz over z squared plus 1 to the n for n a positive integer. We'll do it in the exercise for n equal 2. Okay? So, yeah, and second remark is that also Steve asked me is how do we know how to integrate on which path and what is the function to integrate? This usually comes with practice. Okay, after seeing so many examples, we become familiar with loops and functions, and the path is not unique. Okay, so nothing prevents us, instead of integrating on the upper half circle, to integrate on the lower half circle. Okay, but there's a problem here. I have to change the function to integrate, because now we are working in the lower half plane, so y is negative. So the estimates of part B do not work here. So I have to change a little bit my function to integrate. Okay, and instead I have to take E minus IZ over Z squared plus 1, right? So this is a second method. If you want to work on this lower half circle, we have to modify a little bit the function. And one can proceed exactly as we did. But pay attention to the orientation. Now, we have to take the index with respect to minus I, and this is -1 in this case. Okay? So this is why, so pay attention to the orientation. So I suggest that you do this and compare your results. Okay? So the path is not unique in general, but usually so these two paths, so these two loops are actually equivalent. Why do we prefer the upper instead of the lower? Actually, it's just a convention. Okay, so this works perfectly well. Okay, but usually in the exams, we will give you the path, the loops, and the function to integrate, because when you are in an exam, it's not trivial that you find the right loop. Okay, so, and if you don't guess the right loop, then you will miss your whole problem. So it's not a good idea to leave you on your own. Okay, so we will give you, so don't worry, we will give you the loop and the function to integrate. And you just have to apply properly the theorems and do estimates, okay, in order to prove that some integrals tend to 0 as r tends to infinity. Okay, so you'll be guided. Okay, don't worry. But this is just because since we are just discussing here, now you may invent another loop, of course, but these are the most two natural loops to consider. Okay, now I move to the exercises. So exercise 5, find all holomorphic functions from C to C whose derivative is modulus of z squared. Okay, this is a typical question. We always ask such questions in the exam. But when we ask you such questions, there are two possibilities. Either there are no such functions, or there are very few. Okay? In this case, let us think a little bit. We want to find an antiderivative of modulus of z squared. Now, if this was true, f is holomorphic, so the derivative should be holomorphic on C. But modulus of z squared is only holomorphic at 0. So this is impossible. So there's no such function. Okay? So this is something very important because it tests your understanding. Okay, the derivative of a holomorphic function is a holomorphic function. Next exercise about the maximum principle. Consider a holomorphic function on the open disk of center 0 and radius r. And for each circle inside the disk, let capital M of R be the maximum. This could be a maximum because it's a compact set and modulus of f is continuous. So you can write maximum if you like. So it's the maximum of the modulus of f on the circle of radius r. So it depends on r. We have to show that this function is non-decreasing or increasing if you like. So when the radius becomes bigger, this increases. And second question, if m of r1 equal to m of r2, then f is constant if r1 is less than r2. Okay. Now, by the weak maximum principle, m of r is the supremum over the disk of center 0 and radius r, because this is the boundary of that. Okay, and we are working on a connected set or an open connected bounded set B0R. Now, when we write this in this way, it's easier to prove that the function is increasing, because when we increase the radius, the disk becomes bigger. So the disk of radius R1 is included in the disk of radius R2, and therefore the maximum here is less or equal than the maximum here. And that's it. That's very easy. Now, I could not have done this if I just take modulus of z equal r, because when the radius increases, there's no relation between the two circles, but there is an inclusion relation between the disks. Okay. Now, second question. Suppose that m of r1 equal m of r2 for r1 less than r2. Okay. Since modulus of f is continuous on the compact disk, on the closed disk of center 0 and radius r1, then modulus of f has a maximum value inside the disk, or at the disk, maybe at the boundary. Okay, because this is a theorem of topology. A continuous function on a compact set is bounded and has a maximum and achieves a maximum and a minimum value. Okay, so we have a point A inside, so not inside, on the disk, so it could be on the boundary. So call it A. So this supremum, so f of A is the maximum, if you like. So what do we have? We have the disk, the closed disk of radius r1 is contained in the open disk of radius r2, because r1 is strictly less than r2. So modulus of A, so modulus of f achieves a maximum value at A. And therefore, by the strong maximum principle, f is constant on the bigger disk. Okay? And the principle of analytic continuation tells me that f is constant on the original domain of f, on the bigger disk. So we have b prime 0 r1 contained in b0 r2 contained in b0 r. Okay, so it's just an easy application of the strong maximum principle and the weak maximum principle. And this is a typical question in the exam. Next exercise, also about the maximum principle. So consider a continuous function on the closure of an open and bounded set, which is connected, and holomorphic inside. So continuous up to the boundary and holomorphic inside. If modulus of f is constant on the boundary and f has no zeros, then f must be constant. So we have two assumptions. Okay, three assumptions actually. We have holomorphy, constancy on the boundary, and no zeros, so f does not vanish on omega. We must show that f is constant. Okay. If you remove one of these conditions, the result may be wrong actually, and I encourage you to give counterexamples. So give me an example where f has a zero, but f is not constant. It's very easy to construct such thing. But I have a combination of three strong properties. Okay, if f has no zeros, then I may consider actually, so okay, let us start by eliminating the trivial case. Okay, so f is constant on the boundary, right? This is, yeah, so this is z on omega bar, this is z on the boundary. Okay, so it's c actually. So the maximum of modulus of f is c, because by the weak maximum principle, okay, the maximum at the boundary is the maximum everywhere. Okay, so we have that modulus of f of z is less than c for all z and omega bar. Now, if c is 0, then f is 0, right? So it's constant. So this is not interesting case. So assume that c is positive. Okay. If f has no zeros in omega, then I may consider 1 over f. And 1 over f in this case would be holomorphic, because as the inverse of a holomorphic function which does not vanish. Okay, now since f has no zeros on the boundary, because f is constant and the constant is positive, so actually 1 over f is still also continuous on omega bar. So now I can apply the maximum principle to 1 over f. The weak maximum principle applied to 1 over f tells me that the maximum on omega bar is the same as the maximum on the boundary, and it's 1 over c because on the boundary f is equal to modulus of f is equal to c. Okay. Therefore, 1 over z in modulus is less than 1 over c. So when I reverse the inequalities, so I get modulus of s is bigger than c, which is positive. Okay, so what do I have here? Modulus of f is less than c and bigger or equal than c. Therefore, it's constant. So it's equal to c. Now, if the modulus is constant, you should have done an exercise in Math 209, the first course on complex variables, that if the modulus of c is constant, then f is constant. Okay? But and also you can use the strong maximum principle if you like. If you don't want to use this result, actually we applied this before actually. So if modulus of f is constant on an open connected set, then it's constant. And then f is constant. But you may also use the strong maximum principle, okay? Because if the modulus of f is constant, then the modulus of f achieves a maximum value inside. So f is constant, right? If it's constant on omega, it's constant on omega bar by continuity. So you have two ways to deduce that f is constant from the fact that modulus of f is constant. So this concludes the exercise 7. Okay. Next exercise, Schwarz lemma. We have a holomorphic function from the unit disk to itself, which vanishes at 0. We have to show first that the modulus of f of z is less or equal than the modulus of z. And we gave a hint. We have to consider the function which is equal to f of z over z if z different from 0 and g of 0 equal f prime of 0. Why f prime? Because I need a continuous function. So the limit of this, since f of 0 equals 0, this is Newton's ratio. So it converges. So it's f of z minus f of 0 over z minus 0. And yeah, this is the hint, just the hint. So if I want g to be continuous, I must set g of z equal at 0 equal f prime of 0. Okay, so G is continuous now and holomorphic on the disk, on the punctured disk without its origin. But I know from a previous corollary in the lectures that actually this implies that G is holomorphic. Okay? If it's holomorphic on an open set without a point and continuous on that set, then it's holomorphic. So if you like, we say that 0 is a removable singularity. In the next chapter, we'll call it removable singularity. Okay, now take a positive number r less than 1 strictly and apply the weak maximum principle to the closed disk. Yeah, this is just G, there's an error here. This is G of Z. The supremum of the modulus of G, since G is holomorphic, inside the disk is the same as the maximum on the boundary. So this is G of Z. But on the boundary, G of Z is f of Z over Z. Okay, so there's an error here. This is G of Z. Now, modulus of Z here is equal to R. And the modulus of f is less than 1. Right? If now Z is in the open disk, then for any R between modulus of Z and 1, according to what we said, we have G of Z less than 1 over R. And this is true for any R. So if I let R tend to infinity, I get at the limit modulus of G of Z less or equal than 1. And that's it. But G of Z is f of Z over Z, so modulus of f of Z is less than the modulus of Z. Now, why modulus of Z of f of Z is less than 1? Because f maps the unit disk into itself. So by assumption, f of Z is in the unit disk, so its modulus is less than 1. It's not true for any holomorphic function, but we are considering a function mapping the disk into itself. Now, this the second question. This is B actually. If we have equality in part A at some point, then actually f of z is a multiple of z. So by a complex number. And by the way, what is the geometric interpretation of this? You should know it. If lambda has modulus 1, then we can write it as e to the I alpha. And multiplying by e to the I alpha is just a rotation of angle alpha. So what we are saying here is that if f is holomorphic from the disk to itself, vanishing at 0, and fixing the norm of one element, if you like, then f must be a rotation. Okay. So if modulus of f of z0 equals z0 from of course z0 different from the origin because f of 0 is 0. So this, okay. If this is true, then when I divide by z0, I get g of z0 equal 1. So what does it mean? It means that g now achieves a maximum value at the point z0, which is inside the open disk. And the strong maximum principle tells me that g is constant. If g is constant, call this constant lambda, okay, which is a complex number. Now, because modulus of g of z0 is 1, then the modulus of this constant should be 1. And since g of z equal f of z over z, then we should have f of z over z equal lambda for all, of course, provided z different from 0. And therefore, f of z equal lambda of z for z different from 0. Now, but this equation actually is still true for z equals 0 because f of 0 equals 0. Okay, or you may invoke continuity. So I have f of z equal lambda of z for all z in the unit disk. And this is the result. So f is the rotation of center 0. Next exercise, it's very important. We have to show that the real and imaginary parts of f are harmonic of a holomorphic function are harmonic. What do we mean by harmonic? It means that there are enough differentiables to talk about second derivatives, so C2 if you like, and the Laplace operator of u is 0. The Laplace operator or Laplacian is just the sum of the second order partial derivatives. Okay? So we have to prove that the real part of f and the imaginary part satisfy this equation. And this is a fundamental property of holomorphic functions. Okay, it's not difficult actually because this is a consequence of the Cauchy-Riemann equation. But we have to justify something because when we defined the holomorphic functions, we said that a holomorphic function is just C differentiable. Okay, so the real and imaginary part are just differentiable, right? Are differentiable. But we know now that actually they are more than differentiable. They are C infinity. Okay, so if you stick to the definition, I know that the real and imaginary part are R differentiable and satisfy the Cauchy-Riemann equations. And I know this. So we can write the derivative. If you recall from chapter 1, the derivative of at z can be written as the partial derivative of the real part over x plus I times the partial derivative of the imaginary part over x, or the other way around. So you can write as you like, because by the Cauchy-Riemann equation actually. So del u over del x is del v over del y. This is the first Cauchy-Riemann. And del u over del y is minus del v over del x. Okay, these are the Cauchy-Riemann equations. But now we know from the theory of chapter 2 that f prime is holomorphic. Okay, so if f prime is holomorphic, then the real part and the imaginary part are differentiable. So all the partial derivatives are differentiable. So actually, u and v are of class C2. Okay, And if you continue this reasoning, you differentiate one more time, you will see that the partial derivatives are differentiable of all orders. Okay? So actually, the real part and imaginary part are C infinity, not just C2. So now I can talk about the Laplacian of them. Okay? We didn't know that in chapter 1. Okay? But the theory of chapter 2 tells me that F has all derivatives of all orders, and therefore U and V have derivatives of all orders. Now, to prove that the Laplace operator of U is 0, okay, we just apply Cauchy-Riemann. Take the first one, del U over del X equal del V over del Y, and differentiate both with respect to X. So we get del U square over del X square equal del square V over del X del Y. Okay, and if you take the other equation and differentiate with respect to Y, you will get minus the opposite, minus the result of the first one. Now, since V is C infinity, these mixed, so this mixed partial, so the mixed partial derivatives are equal. So the order is not important here. If I differentiate first with respect to X and then with respect to Y, or vice versa, I get the same result. This is known as Clairaut-Schwarz theorem, okay, that you may encounter in first year. Okay, so now we just add the two, okay, because the second order partial derivatives are opposite. So when I add, I get 0. Okay, and I can do similarly for the imaginary part. Okay, they play the same role. So if I repeat the same reasoning, if I differentiate now with respect to Y and then with respect to X, I get the same thing. So conclusion, the real and imaginary part of a holomorphic function are harmonic. And the study of harmonic functions is a big field actually in mathematical analysis. Okay, by the way, this equation Laplacian of U equals 0 is an example of what we call a partial differential equation. Okay, so it's a differential equation, but it involves two independent variables instead of one. Okay, so the solution is a function of two variables rather than a function of one variable. So it's called a partial differential equation. Okay, so this concludes exercise 9. Exercise 10 is an application of Cauchy's inequality. And we ask such questions in the exam. Okay, so we have an entire function, which means a holomorphic on C, which is bounded in modulus from above. So we say that a function satisfying this inequality is said to have a polynomial growth at infinity. Okay, so the modulus of F is bounded from above by some polynomial in modulus of Z. Okay, we have to show that F is a polynomial of degree at most P. So F cannot be, the power series of F cannot be infinite. Okay, now this is easy because we just apply Cauchy's inequality to any circle. So take any circle of radius R, and we know that the Cauchy's inequality tells me that, so if I write f of z as sigma of a n z n, so I do I expand f in a power series about 0. So what is a n? A n is the coefficient of the power series. Okay, so f of z is sigma of a n times z to the n. And Cauchy's inequality from the lectures tell me that the modulus of the coefficients is less than what? The maximum of f on the circle divided by r to the n. Okay. Now, the modulus of f on the circle is less than this. So when modulus of z equal r, just replace it by r. So I get a constant, which is not important, times 1 plus r to the power p over rn. And now it's easy to conclude, because now if n is bigger than p strictly, this tends to 0 when r tends to infinity, because r was arbitrary. And actually, we used such argument when we proved Liouville's theorem. Okay, so when n is bigger than p, this term tends to 0. So but this is constant. This does not depend on R. So I get an equal to 0. And therefore, the only possible non-zero terms are a0 up to ap. So this means that f is a polynomial of degree at most p. Okay. And that's it. So this concludes the video. In the next video, we are going to solve the remaining exercises. So thank you for your attention.